Learning objectives. In this chapter, the user would learn the following in detail: finite differences, Newton interpolation formula, Lagrange's interpolation formula. The finite difference is the discrete analog of the derivative. The finite forward difference of a function fp is defined as delta fp approximately equal to fp plus 1 minus fp is called equation number 1. And the finite backward difference as delta fp approximately equal to fp minus fp plus 1 is called equation number 2. The forward finite difference is implemented in Mathematica as difference delta in closed interval f, I. If the values are tabulated at spacings h, then the notation fp approximately equal to f of x0 plus ph approximately equal to f of x is called equation 3 is used. The forward difference would then be written as delta power k fp. Similarly, the kth backward difference as delta k fp. However, when fp is viewed as a discretization of the continuous function f of x, then the finite difference is sometimes written delta x approximately equal to f of x plus 1 by 2 minus f of x minus 1 by 2 is called equation number 4. 2 times of odd impulse pair of x into f of x is called equation number 5, where star denotes convolution and the symbol is called the odd impulse pair. The finite difference operator can therefore be written delta approximately equal to 2 into odd impulse pair of star as nth power as a constant, nth finite difference. For example, take n equal to 3 and make a difference table. Figure convolution and impulse pair. Newton's interpolation formula. Making use of forward difference operator and forward difference table will be defined a little later. This scheme simplifies the calculations involved in the polynomial approximation of functions which are known at equally spaced data points. Divided difference table. X, Y. X follows x1, x2, x3, x4. Y follows y1, y2, y3, y4. First divided difference table. F of x1, x2 equal to f of x2 minus f of x1 divided by x2 minus x1. F of x2, x3 equal to f of x3 minus f of x2 divided by x3 minus x2. F of x3, x4 equal to f of x4 minus f of x3 divided by x4 minus x3, then 0. Second divided difference table. F of x1, x2, x3 equal to f of x2, x3 minus f of x1, x2 divided by x3 minus x1. F of x2, x3, x4 equal to f of x3, x4 minus f of x2, x3 divided by x4 minus x2, then 0, 0. Third divided difference table. F of x1, x2, x3, x4 equal to f of x2, x3, x4 minus f of x1, x2, x3 divided by x4 minus x1, then 0, 0, 0. Newton's divided difference interpolation formula. F of x equal to f of x0 plus x minus x0 into x0 x1 plus f of x0 x1 plus x minus x0 x minus x1 f of x0 x1 x2 plus etc. Newton's Gregory backward interpolation formula. Y equal to yn plus u into delta yn plus u into u plus 1 by 2 factorial del square yn plus u into u plus 1 into u plus 2 by 3 factorial del cube yn. Given sin 45 degree equal to 0.7071, sin 50 degree equal to 0.7660, sin 55 degree equal to 0.8192, sin 60 degree equal to 0.8660. Find sin 52 degree. Solution. Newton's Gregory formula for forward interpolation is f of x equal to f of alpha plus uh equal to f of a plus u into delta f of a plus u into u minus 1 into 2 factorial del square f of a plus u into u minus 1 into u minus 2 by 3 factorial del cube f of a. Here x equal to 52 degree, a equal to 45 degree. Then u equal to x minus a divided by h equal to 1.4. Let us form the difference table. The difference table by x, f of x, then delta f of x, then del square f of x, del cube f of x. X follows 45, 50, 55, 60. Then f of x follows 0.7071, 0.7660, 0.052, 0.032, 0.0468. Then delta f of x follows 0.0589, 0.0532, 0.0468. Then del square f of x follows minus 0.0057, minus 0.0064. Then del cube f of x follows minus 0.0007. Finally, f of a equal to 0.7071, delta power 1 into f of a equal to 0.0589, del square f of a equal to minus 0.057, del cube f of a equal to minus 0.0007. Substituting in 1, we getting f of 52 degree equal to 0.7071 plus 1.4 into 0.0589 plus 1.4 into 1.4 minus 1 by 1.2 into minus 0.0057 plus 1.4 into 1.4 minus 1 into 1.4 minus 2 divided by 1 into 2 into 3 into minus 0.0007. Then we getting 0.7071 plus 0.08246 minus 0.001596 plus 0.0000392. Then finally 0.788032 approximately. Example 11. Given, find f of 75. Solution. The value to be interpolated lies at the end of the given values, hence we use Newton's backward formula. Difference table. X, f of x, delta f of x, del square f of x, del cube f of x, del power 4 f of x. X follows the values 1, 2, 3, 4, 5, 6, 7, 8. F of x follows the values 1, 8, 27, 64, 125, 216, that is called 216, 343, 512. Delta f of x follows 7, 19, 37, 61, 91, 127, 169. Del square f of x follows 12, 18, 24, 30, 36, 42. Del cube f of x follows 6, 6, 6, again 6, again 6. Then del power 4 f of x follows 0, 0, 0, 0. Hence x equal to 75, a equal to 8, h equal to 1, u equal to 7.5 minus 8 by 1 equal to minus 5. Hence, a now by Newton's backward interpolation formula. F of x equal to f of a plus nh equal to f of a plus u into delta f of a plus nh plus u into u minus 1 by 1 into 2 into del square f of a plus nh plus u into u minus 1 u minus 2 divided by 1 into 2 into del cube f of a plus nh. Higher differences vanish. Equal to 512 minus 0.5 into 169 plus minus 0.5 into minus 0.5 plus 1 by 1 into 2 into 42 plus minus 0.5 into minus 0.5 plus 1 into minus 0.5 plus 2 divided by 1 into 2 into 6, then equal to 512 minus 84.5 minus 5.25 minus 0.375, then we getting finally 412.875. Conclusion. In this chapter, we have covered the following in detail: finite differences, Newton interpolation formula, Lagrange's interpolation formula,